Hello students, today we discuss about the revision of Unit 2. So Unit 2 consists negative binomial distribution, geometric distribution and hypergeometric distributions. So these are the continuity concepts of Unit 1 like binomial and Poisson distributions. Almost all the distributions are extended to binomial and Poisson distributions only. First, here we discuss the geometric distribution. It's the extension of our binomial distribution. So in geometric distribution, x can be defined as number of failures before the first success. So varying probability p constant for each trial. It can also be defined as number of trials required for getting the first success. So like number of balls required for a cricket bowler to make the batsman out, like. So number of trials is considered. Suppose a boy is felting stones at a mango tree. Number of failures before hitting a mango is one of the geometric distribution. There are two kinds of geometric distributions. One is based on the failures, another is based on the trials. So if x is a random variable represents the number of failures before meeting with the first success, then the PDF is given by p of x is q power x into p. X starts at 0. So p plus q is 1, p greater than or equal to 0, q less than or equal to 1. These are the routine. So number of failures are there, that's why x starts from 0 onwards. Number of trials case in the sense x starts at 1. There q power x minus 1, like that consider. It is the second kind of geometric distribution based on number of trials. P of x is q power x minus 1 into p. So basing on that, here derive that summation q power x is 1 minus q power minus 1, like that. So derive the moments of geometric distribution. One more thing observe. So without mentioning any kind in the sense, that considered as the first kind only here. So the Pmf of geometric consider mu r dash mu 1 dash first expectation of x summation x into p of x, like that. So it's a q by p is the mean of geometric distribution. Then mu 2 dash find expectation of x square. So one more thing observe, these are the expansions, that's why. So x square expansion I consider expectation of x into x minus 1 plus expectation of x. First derive the expectation of x into x minus 1, then expectation of x consider from that. Mu 2 dash is like that. Then mu 3 dash is expectation of x cube expansion consider x into x minus 1 into x minus 2 plus 3x into x minus 1 plus x. All the expectations substitute here and simplify. It gives like this mu 3 dash. Then mu 4 dash is expectation of x square expansion consider and substitute. Easily can get mu 4 dash. After getting the mu 1 dash, mu 2 dash, mu 3 dash and mu 4 dash, there he considers central moments. Mu 1 is 0, mu 2 is mu 2 dash minus mu 1 dash whole square. Substitute and simplify q by p square. Like mu 3 consider and substitute and simplify. So mu 4 also you should do. Then beta 1, beta 2. Like that substitution and simplifications only. You should remember one thing. P plus q is 1. Q is 1 minus p. P is 1 minus q, like that. Then beta 1 also fine. Beta 2 also fine. Then like derive MGF of geometric distribution. Hence find its mean and variance. So p of x consider, you know that MGF is mx of t, expectation of e power tx, summation e power tx into p of x. P of x substitute and simplify. Then differentiate with respect to t and substitute t equal to 0, get mx dash of t. Again differentiate with respect to t, mx double dash of t there I'll get. There put t equal to 0 and 1, we get mu 1 dash mu 2 dash. Then mu 2 is mu 2 dash minus mu 1 dash square, it gives the variance like. So see here, once we consider like that, so it's without mentioning the kind, it's the first kind only. Then characteristic function of geometric distribution also like that only. Then cumulant generating function of geometric distribution, hence obtain its mean and its cumulants and moments. It's another very important generating function. First consider the MGF of geometric distribution. You don't know in the sense, again you should derive based on our PMF all. So once you consider MGF, then CGF is kx of t is log mx of t. Substitute and simplify here. Then how to get k1, k2, k3, k4 in the sense differentiation only here. So one time differentiation kx dash of t. So there you substitute t equal to 0 in the sense it gives mean as well as a first cumulant. So after that kx double dash of t consider. So and simplify it, it gives that mu2 directly. So mu2 is k2 equal to kx double dash of t at t equal to 0 like. So q by p square like. Then additive property is another repeated concept here. So n independent geometric variates is a negative binomial variate. So n independent geometric variates consider mgf of n independent geometric variates sum is negative binomial PGF. There will get mx of 1 mx1 of t consider mx2 of t consider mxn of t like. By using the additive property of mgf, m summation xi of t consider and substitute it, it is of the form of mgf of nbd. That's where you can apply the negative binomial distribution also. Then like this, then recurrence relation for the probabilities of geometric distribution is repeated one only, very easy like. Then problems are also important here. An unbiased die is tossed until the occurrence of a 6. Find the probability that the number of trials required in all is more than 6. P of x greater than or equal to 6. So there will be fine. So first Pmf of geometric distribution P of x is q power x minus 1 into p. X starts from 1 to like. Here it's related to number of trials. That's why consider the second kind q power x minus 1 into p. X from 1 like that. So q is p is 6. What is the probability of getting 6 when a die is rolled in the sense 1 by 6. So q is 1 minus p. 1 minus 1 by 6. 5 by 6. Then p of x consider q power x minus 1 into p. So basing on that p of x greater than 6, p of x greater than or equal to 7 is also considered, no issue. 7 to infinity. So 5 by 6 power 6 considered as common. The remaining is of the form of 1 plus x square plus 1 minus x power minus 1 consider and simplify it. It gives some value like. Then these are the expansions. These expansions also you should remember like this. This is the another very important and frequently repeated concept in geometric distribution. Define geometric distribution, state and prove memoryless property or lack of memory properties of geometric distribution. So in our stats paper 2, there are two memoryless properties, one for exponential distribution, another for geometric distribution. Both are nearby only. So once you apply the condition also, there is no condition in the RHS. That's why these two are not having the memory. So like that they will consider the memoryless property. First you should define the geometric distribution here. So p of x is q power x into p. X starts from 0, 1 to 1. Summation p of x is 1. Basing on that there should go through that. Memoryless property or lack of memory properties of geometric distribution consider. First a statement is if x follows geometric distribution for k greater than or equal to 0, y equal to x minus k as the geometric distribution, then we can show that p of y equal to t given that x greater than or equal to k is equal to p of x equal to t. Once we apply the condition like x greater than or equal to t also, there is no use, it gives without condition. So which implies that the additional time to wait as the same distribution as initial time to wait. So that Pmf of geometric distribution consider p of x equal to t, instead of the x consider t. So p of x greater than or equal to k consider. So summation x equal to k to infinity p of x. Summation x equal to k to infinity q power x into p. P consider as common. The remaining is like. So 1 plus q square like that. That's why p q power k into 1 minus q power minus 1. 1 minus q in the sense p get cancelled. The remaining is q power k. Like then p of y equal to t given x greater than or equal to k. It's conditional probability p of a given b. P of a intersection b by p of b. So p of b already derived. In p of a there are to find p of y equal to t intersection k x greater than or equal to k. So here we consider what's the given condition in the sense y is x minus k nana. So x minus k equal to t intersection x greater than or equal to k ma, x equal to k plus t intersection x greater than or equal to k ma, x greater than or equal to k in the sense k comma k plus 1 comma k plus 2 and so on, k plus t ma. So k plus t plus 1 like that. So that's why what's the common term here is x equal to q, k plus t is the common. That's why p of x equal to k plus t consider there. So instead of the x, consider k plus t. Q power k plus t into p is the probability of that. So simplify this, then go through. So after simplification, the LHS is q power t into p. RHS is also q power t plus p. So both are equal. P of y equal to t given x greater than or equal to k is p of x equal to t. So no condition involved in the RHS. That's why there is no memory for geometric distribution. This memoryless property is one of the important and easy one. Be serious and prepare this. Okay, thank you.